Hello, today we're going to be doing Chapter B, or Class B, Snell's Law. And we're going to look at two approaches, one using geometrical optics, where light travels in straight lines, and a derivation which uses the wave, or physical optics. So this is very, very neat to see a derivation in both ways, with geometrical optics, light travels in straight lines, and physical optics, where light travels as waves. The wave one is actually the easier one, and it's often taught in high school using geometry and trigonometry. The geometrical optics one is the more sophisticated one, mathematically speaking, and that's using the principle of least time of Fermat, which we introduced in our previous class. And then we'll look at some applications with total internal reflection, fiber optics, and the mirages. Here's a picture of a hydrogen balloon that has exploded. This is from astronomy class from many years ago when we were talking about chemical reactions. So we had a balloon filled with hydrogen. Now, a professional did this preparation for us, so be very, very careful. You don't want to do this, never do this at home on your own. Hydrogen is very, very dangerous, like the Hindenburg that caught on fire, for example, in New Jersey in the 1930s. So here, we very carefully, Dr. Booker was working on this, had someone put a match, he taped the match on the top of a meter stick, and the student then put the meter stick up, and the balloon was on a string and then exploded. And this is nice optics because, see, the temperature variations in the air due to the heating cause different index of refraction at different places, so the light then did some interesting shimmering effects, and that's known as a mirage when that happens, when due to different index of refraction in different places, the light does interesting things. We're going to be looking at that today. We're going to look at B1, Snell's law. And first we're going to do a high school derivation, one that uses trigonometry. Let's do this by way of an analogy. See, we're basically interested in going from, say, air to water, or air to glass. And I want to show you that the light is going to bend toward the normal. So by analogy, we're going to look at here folks that are marching on grass, and then there's mud. So if you have folks that are coming in at an angle like this, and they're marching, when this one hits the mud, this is going to go traveling slower in the mud, and these folks are going to be able to walk, faster. So what happens when you get to the mud, you get something like this occurring, where these folks are still, going faster on the far right. Now this diagram is hard to draw, so we're going to look at one that is picture perfect. So at the picture perfect one, you can see here that the distance between one of the rows of the marching folks to the next one, that is going to be your wavelength. And this is going to be the wavelength in the grass. We'll call that 1. Then here, when they hit the mud, see, these folks are going to go slower, and the effect is that the wavelength here in the mud that's going to be shorter because they're not traveling as fast. So here, what is really neat to look at is a conservation of people, that if your eyeballs here watching, let's say down here and up there, if so many people go by per second, that has to be the same down here because people aren't being created or destroyed. Conservation of people. So here, since they're traveling faster, there's more separation. And then here, they're traveling slower, there's less separation, so that the number of people that pass any given point is going to be the same. So here, this problem is very, very nice. You can think of, for example, by the way, if you have, say, asphalt and mud, and a car is going like this, that this wheel that hits the mud, this one's traveling faster, it's going to like swerve around, and it's going to like swerve and like bend toward the normal. So if you have this normal, it's just perpendicular to the interface, then you're going to bend toward the normal. So that's the law of refraction that we're going to be looking at. So how about some parameters here? Well, the wavelength, lambda, is the distance from one road to the next. So that would be, if you have like a wave, and these are your crest, like your crest and your troughs, for example, you're looking like down from above, that's the wavelength. And then the frequency is how many rows pass per minute, or usually we use per second. And T, capital T, is the period, the time for one cycle to occur. So here's a neat little rule. If, for example, you have something that takes a half a second for it to occur, then your frequency, you're doing 2 per second. You just flip it. So you just flip this number. So the formula is, the frequency is 1 over T, and T is 1 over F. And look, you flip the units too, see? T is in seconds, and the frequency is per second. And, per second, we abbreviate as Hz, which is the hertz. So if you have a wavelength and you're going to have the event, the cycle be the period T, then you can think of the velocity as the wavelength divided by the period, just like you have distance over time. So since the reciprocal of the period, or 1 over T, is equal to F, you can write this as lambda F. Another way of looking at this is you have someone here like surfing, and this is, say, 10 meters. It's 10 meters that go from one crest to the next. And if someone's watching this here and say 5 go by per second, well then, like, you're traveling 50 meters per second, because like 5 of these go by per second, or 10 each. So that's one way to see this immediately. This is your 5, and there's your 10, and you multiply. So a lot of ways of seeing these relationships. So let's go on and work on this derivation. And here, without drawing the soldiers, but just drawing, say, here the straight lines. This is fairly easy to do, straight lines like this. All right, then here, this is a wavelength 1, and there's a wavelength 1. And then here you're going to turn like this. And if we do this perpendicular there's your wavelength 2, there's your wavelength 1. And your angles, if you have your normal here, the angle theta 1 is going to be this angle. And if you have, your normal is your perpendicular with your interface. So this is your grass, and this is your mud. Then this is theta 2, and you can see that if you have this distance d here, and these are right triangles, that this distance d is your hypotenuse. So if you look at this little angle in there, that's the same as this angle over here, since that angle's complement to this one. 90 degrees, they're complementary, and since you have the right triangle, the complement's over here. So this angle here is your theta 1, and the sine of theta 1 is going to be your opposite, your lambda 1 divided by your hypotenuse, d. And then here, same thing applies. If you have this angle here, whatever this angle is here, this angle is going to be complementary to this angle over there. And I would say for here, you're doing the same sort of situation where you're looking at this angle theta 2 is going to be the same as this angle in here. Okay, so it's a little tricky to draw these accurately, so let's go ahead and look at the one that's already in our book. This is your angle of incidence, this theta 1. Okay, here, this is your normal. And here, this angle theta 1 is complementary to this angle in here. But that angle is also complementary to this one because of the right triangle. So you got your 90 degrees here, which means these are complementary. And since you have a right triangle, this complementary, so that's also theta 1. Then here, for theta 2, this angle theta 2, since this is a 90 degree angle here, this angle in here is complementary to your angle at theta 2, but since this is a right angle here, you got theta 2 there. I had an optics teacher many years ago that said these things are either going to be complementary or the same. So if you were to imagine, bringing this back up, so this collapses, this theta 1 collapses, then this one gets bigger, but then what's going to happen when you bring that back up like that, bring it down, this is going to collapse. So you're going to collapse the two. Yeah, the optics teacher said, like, if you were to like straighten this out, like, see, if you straighten this bottom one out by going like this, then you could see this theta 2 goes to 0, and so does this theta 2. So he said they're going to be equal. Well, that's not a formal proof, but since these things are either complementary or the same, that does work. And then here, if you were to bring this down over there so that this theta 1 closes, then this theta 1 closes. But the complementary angles that I gave you, they're the most precise way of doing it. This is complement to this, that's complement to there, so these are the same. So then you have this nice relationship that lambda 1 is equal to d sine theta 1. And then lambda 2 here is d sine theta 2. All right, so now let's go back and regroup. We have V1 is lambda 1f, and V2 is lambda 2f, all right? So that means V1 over lambda 1 is f, but also V2 over lambda 2 is f. And now we use the rule that we figured out here, the relationship that lambda 1 is d sine theta 1, and lambda 2 is d sine theta 2. So therefore we can write this as V1 over d sine theta 1 is V2 over d sine theta 2. And you can cancel the d's here. So we're going to cancel the d's and have V1 over sine theta 1 is V2 over sine theta 2. Now here's a definition. The index of refraction, n, is by definition, is equal to the speed of light in vacuum over the speed of light in the material, where light's going to slow down when it goes through stuff. So if this is the case, then we can write down V as C over N. So then we have here, for V1, we have C over N1, that's the V1, and that's over the sine of theta 1, and that's going to be equal to C over N2, and this is 1 over the sine of theta 2. The C's cancel out here, and if you cancel out the C's and then write down the reciprocal, you have this famous Snell's law. That's it. That's the derivation of Snell's law using trigonometry. So you bend here toward the normal when you have something fast up there, and then you're going to go slower. And notice that the ants have figured this out, that the ants here where they can move fast are pretty much going like in a straight line there. And then when they go into the mesh and have trouble, they then turn down like that. So that's your case here where you have your angle of incidence, theta 1 and theta 2, and the ants, in getting from, say, upper left to the lower right where the food is down here, they're using the law of refraction. Isn't that cool? Now this law of refraction goes back many years. We have Ptolemy, Greek mathematician and astronomer, and that's like going back 2,000 years, roughly. But then we have the Arab science, Persian and Arabic science, which dominates during the Western Middle Ages. So when you have the Dark Ages, for example, in the West, Arabs are flourishing with science. And naming stars, a lot of the stars have Arabic names. And here, Al-Haytham here got very close in his book of optics to the law we just derived. Ptolemy had a relationship for small angles, but then it was Ibn Sal here who nailed it and discovered the law. And we only learned about him recently because of Rashid's research. This historian of science does research into Arabic and Persian science, and he found this the case. So when the West has their scientific revolution with Copernicus, they kind of rediscover the law. So here we have Thomas Harriot, English mathematician and astronomer, rediscovering the law independently, 1602. And then Snell, which we usually write with 2 L's, a rediscovery, 1621. And since these weren't published, Descartes rediscovers it, 1637. And then with Fermat, we have the principle of least time, which is a very elegant way to derive the law. But the law has already been established by the previous scientists earlier. So let's see if we can do the problem where we use the principle of least time. Very, very beautiful connection we make here between the wave and the straight line way of thinking. So here, when we go to Snell's law here, and this is going to be Fermat derivation. This is going to be geometrical optics. The one we just did was physical optics, where we had waves. We had these waves like this with the wavelength, and notice that the waves, though, travel they have an arrow like a geometrical optics kind of array with them. So remember that physical optics includes geometrical optics. But what we're going to do here for Fermat's derivation is I'm not even going to be using waves. So that is really nice. So this is going to be like really a geometrical optics derivation. And the one we had just seen here earlier was with physical optics. So if we look at this situation where we want to go from, say, a point that's a certain distance away from the boundary, and we could say this is the sand and this is the water, and there's someone down here that needs help, save me. So we're going to look at somebody here is going to run more, and then there's going to be, a bend to get there in the shortest time. You're going to run more and then like turn and swim less, since you go slow in the water and you go fast here. So let's set this up, and the point that we're going to finally get to, say, is a distance d away like this, and this angle here is theta 1 and this angle here is theta 2. And let's say that this is x, this distance here, so that this is d minus x, this distance there. And we want to get there in the shortest time. Well, there's going to be a time, say this is d1 and say this is d2. We get the two distances. And remember that your velocity is your distance divided by time. And that means that if you want your distance, you can think of your distance as your velocity times time. And if you want your time, you can think of your time as your distance divided by velocity. So like depending on which one you want to go for, you got these three forms. Well, we want the time, T1 here and, the T2 down there. So we want the total time is going to be the time of the running in the sand plus the time swimming in the water. So that's going to be a d1, this distance at velocity 1, and then d2, the swimming distance over velocity 2. And we would like to get prepared with the index of refraction form. So remember that n is c over v. So that means 1 over v is n over c. So let's put all this together. D1 is going to be your Pythagorean theorem here, where you're looking at d minus x, and then you're looking at y. Let's call this y1 and call this y2. All right, this height there. So this would be then the square root of d minus x squared plus y1 squared, and that's going to be divided by v1. And then the second distance is going to be x and y2. So that's x squared plus y2 squared, and that's over v2. Now, if you want to get rid of the v's, we're going to use the n there. So this is n1 over c. Okay, 1 over v1, n1 over c. And this will be then get rid of the v. And this is then d minus x squared plus y1 squared. And this is n2 over c. And this is x squared plus y2 squared. And now we're ready for the calculus. So see, this t is a function of x, and we want to make it so that we get a minimization. So we want to set the dt dx equal to 0. So if we do that, this is a constant, n1c, and if you take a derivative of all this stuff with respect to x, you pop it down in the denominator, because this is one of those deals where you have like something to the 1/2 power. So you bring the 1/2 power down, and then you have the same thing with the minus, 1 minus 1/2. And then you use the chain rule and put the derivative of what's inside. So if we pop all this downstairs like this, and then use the chain rule, the derivative of this stuff inside with respect to x is going to be, here you got your 1/2. So the 1/2 is going to be there for, pulling the 1/2 down. And then you're going to have here 2d minus x with a -1, because if you take the derivative, and here you got the 2 come down, d minus x, and the derivative of the minus x with respect to x is going to be the -1. So nice little review of calculus going on here. And then plus m2 over c, the 1/2 comes down. This goes in the denominator, and taking the derivative here is easier. It's just a 2x. And this has to equal 0. So notice that the 2 cancels the 1/2, the 2 cancels the 1/2. Notice that c's cancel here. So you're basically looking at here n1, and since there's a minus sign there, it's going to be equal to 0. I'm going to put this on one side of the equation and that on the other side. So basically you have the n1, and you have the d minus x, and that's going to be over then d minus x squared plus y 1 squared. And then on the right hand side, n2 times x over the square root of x squared plus y2 squared. So if you look at this is amazing, because if you take d minus x, that's this thing. D minus x is going to be this side up here, and that's a right angle. And if you take the d minus x and you divide by the hypotenuse, which is what this is, I mean, that's sine. This is sine of theta 1. All right. And then if you take x and divide by this thing, let's go ahead and blow that up a little bit here so we can see that. So we're looking at something that's coming down like this, and we got this is y2, and this is x, and this is theta 2, all right? And this is, d2. So here, this angle here is the same as this angle there because of the z rule, remember? How I remember it. The z rule, like this. All right, alternating interior angles are going to be the same. So if you take the sine of, if you want the sine of theta 2, you're going to go with the opposite, the x, over the d2. But this is the d2. It's like x squared plus y2 squared. So we're done. We're finished. We got it. We have the derivation, which is the Snell's law, the famous result. So before we go on, let's look here in B3, index of refraction. And if we have index of refraction N is C over V, we have some neat things. If you have, for example, the vacuum, then the velocity is C, so like you get 1. If you have air, it's so close to 1 that we usually just report 1, although later we're going to see, and for homework we're going to be looking at things where you see more precisely what it is. And then water, 1.33, so what does that mean? Well, 1.33, that's a 4/3, close enough to 4/3. So if this is 4/3, it's basically saying that V is 3/4 C, which means the velocity in water is like 3/4 of vacuum. And vacuum has that famous result, 300,000 kilometers per second, which is 186,000 miles per second, the speed of light in vacuum. And then for glass, you have 1.5, which is close to 3/2. So that means the velocity in glass is going to be 2/3 c, because see, the glass is going to be c over vg, and glass is c over vg, and since the n is 3/2 c over vg, that the vg is going to be 2/3 of c. It's kind of neat to see how they're related. This is how I remember it in high school. These are cool numbers. Like there's 2, well, there's 1, and there's 2, 3, and 3 and 4. So it helped me remember the index of refraction for all of these by thinking of water as 4/3, and by thinking of glass as 3/2. And that's a typical crown glass. They're different glasses and types of glasses. And then diamond, the biggie, that is awesome, 2.4, like the highest index of refraction. One of the reasons why diamond rings are nice. So if we look at some of this stuff, say qualitatively, we have said that when light goes from a fast material, like say air, to glass, it bends toward the normal. Now you get some reflection too. You might want to put a reflection in there. Light splits up when this happens. And then if you were to go the other way, say from glass to air, then you're going to bend away from the normal, and you get some reflection in there. So this is ray diagrams, very nice. And then something very wonderful happens with the case where you have, say, glass and you have air like this, and you're bending away from the normal like that, and you get some reflection. If you look at a case where you get, say, steep enough with your angle, then this will skim the surface. It'll bend so much, you'll have a 90, and you'll have reflection. So this case here, going from glass to air, this is considered the critical angle. So this case at the beginning here, these angles are the same, is less than the critical angle. This is the critical angle. And then what happens, if you're steeper than the critical angle, you can't bend away anymore. You already used up all your bending. So you get then a total internal reflection. So when the angle is greater than the critical angle, you get total internal reflection, which makes possible fiber optics. So 2 things make the internet possible. One is the fiber optic here. So when you have something that undergoes total internal reflection, you see, you get this bouncing, 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 bouncing. So this is fiber optics. And the second thing is that the speed of light is so fast. So, I mean, if you look at this, the speed here would take you around the world, if you were to go this fast, 7.5 times in a second. That's amazing. I mean, the circumference of the Earth, like 25,000 miles, and it's like about 7 times 25 gets you 175. So that's just amazing. All right, that you got that speed, and you got the fiber optics. So, and that's what's making this course possible, that you're getting this course here over the internet. Let's look at the case of the critical angle. So you have air, say here's air. Oh, excuse me, you have glass rather. This is glass. Glass times the sine of the critical angle is equal to the index of refraction of air times the sine of 90, which is 1. So that means the sine of the critical angle is the medium you're trying to get into, or bounce, bouncing off of that interface over the starting material. So that would mean here, we're going to actually do this. If you have the sine of the critical angle for the glass, you have NA over NG. This is 1 over 1.5, or 3/2. So this is going to be 2/3. And you then take the arc sine, and if you do that, you get 49 degrees. All right. And the demonstration that we did with the water, where we had here we had, let's go back to our book, we had the water coming out, making a jet stream, and then you had the laser light, doing total internal reflection in the water, similar to the case where you have fiber optics. Good, and then and try to get it so that you can see the green in the beam. So play around with it. Oh, perfect, look at that. That is awesome. Wow. See how bright that is? That's a total internal reflection in the water. The water's the light pipe. It's doing a total internal reflection. And as the water comes out, you're gonna have to probably adjust the laser. Just your guide would be just look at the water in the beam, and if you see it go a little dim like that, then just play with it a little bit so that it like lightens up again. Good. You just got a good angle there. See that right there? Mm-hmm. Now I would have thought that it would really stop by now, but it's still going pretty good. It's still going pretty good. But look, it's still there. Still got some green in the beam. Very nice. Still there. It's almost like a 90-degree angle there, and you can still see some green in the beam. Very good. All right, you could put that cork thing back, or that rubber thing back in there. Nice. Yeah. That's good. We're ready to start B4, Mirages. The Mirage, B4. And the famous road mirage, where you think there's water in the road. When I traveled to North Carolina as a boy with my family, I remember seeing this on the highway. I says, "Dad, why does it appear to be water there?" And my dad said, "Son, that's a mirage." But we're gonna look at this mirage. And one way to look at it as an approximate way, which is actually not the best way, but this kind of a diagram shows you that if you go from slow to faster, because the light's going to travel faster in the warmer air. So here, the light would bend away from the normal, away, and then here I have total internal reflection, and then bend toward the normal, and that's going to explain the mirage. But this is improper analysis at the bottom, because here's where the ray diagrams are not powerful enough. Geometrical optics cannot explain what's going on here. What really happens here is that when you have a wave crest, and you think of the wavelengths, like there's a wave crest, that the wave at the bottom travels faster than the wave crest at the top, so then it then does that turn. So you really don't have the total internal reflection. You have the wave model that explain this better. So there's the Mirage, the water. I always had good feelings toward North Carolina since it was a vacation, so I feel being in North Carolina is a constant vacation. Finally moved here. So let's look at when you apply Snell's law here, and we're going to index of refractions that are getting to be less and less, since the index of refraction on a hot road surface is going to be less than the cooler region. So here you bend away from the normal and away, but look at this. N1 sine of theta 1 is N2 sine of theta 2. But because of the alternating interior angles, the N2 sine of theta 2 is equal to the N3 sine of theta 3. But you can then relate the first one to the third one and bypass the middle one. So when you're doing this over and over again, and get to the point where you're going to have the 90-degree case where you're basically coming in. If you have your normal here, you got a 90, you're coming in at 90, then you can write down that the index of refraction in the cold region where you start times the sine of theta, say, in the cold region is equal to the lowest region, the hot region, and it's going to be the sine of 90, all right? Because when you get down to the lower region, this is basically going to be, your 90 degrees. And then you can just have two parameters. The part that's up here, the cold index of refraction, and then the extreme case at the bottom. So this is your formula where, by definition, the Mirage angle is this angle alpha. An important part that needs to be done is to relate this Mirage angle alpha to the theta. Now, remember that here you can bypass the intermediate steps. Now, here we're approximating the layers of air, which are really, it's a continuous change of temperature. And here we're looking at layers to get the general idea, and then you can take the limit, as these get smaller and smaller. The main conclusion is, as we said earlier, is that N1 sine theta 1 is equal to the one down at the bottom. And if you have 1,000 of these, it's the one at the very bottom. And the one at the very bottom is going to be the one that has a 90-degree angle here, so that your incident angle for the next case would be 90 degrees, and sine of 90 is 1. So therefore we have this nice rule that the n cold sine theta is equal to the n hot sine of 90, which is the 1. But now the question is, what about this theta over here? Well, this theta over here, you can think of this as like, here's a ray of light that's about to go into another, like interface or boundary, and you're approaching with the angle theta, which means you're going to have n sine of theta. That's the Snell's law, equals n sine of theta. All the n sine thetas are equal. So this n sine theta will be equal to the case where you had the 90-degree case and just had the n of the hot. So that's why we have this relationship here, n hot, that had been multiplying sine of 90, which is 1, is by itself, and this is your theta. That's this theta here. And then the alpha is complementary to the theta. So this n cold times sine of theta is going to be equal to your sine of 90, which is 1, and that's going to be the hot surface index of refraction. So we replace this theta with 90 minus alpha, and then that gets us n cold times the cosine of alpha is n hot. So this is the key formula here, which gives us the Mirage angle in terms of the ratios of the index of refraction near the hot road surface and the index of refraction in the cooler region. Now let's look at this cosine of alpha, which is going to be index of refraction hot over index of refraction cold. Alpha is a very, very small angle. And because it's small, we can do an expansion. You remember your Taylor series expansion, your sine of alpha, alpha's in radians, is approximately alpha. And your cosine of alpha, alpha in radians is 1 minus alpha squared over 2. So if we do this, and also it's good to know these, in other words, the tangent of theta is approximately, the tangent of alpha is approximately alpha, because if you take the sine, divide by this, you're basically dividing by 1. This is approximately 1 at a very small angle. So here, if we do this, we get then 1 minus alpha squared over 2 is n hot over n cold. And that means that 1, say, minus the n hot over the n cold is equal to alpha squared over 2. And 2 times 1 n hot over n cold is equal to alpha squared. So alpha is equal to the square root of 2, 1 minus the hot over the cold. That's the Mirage angle. So back in 1863, the chemists Gladstone and a Reverend Dale, discovered that the index of refraction, -1, is proportional to the density. Here we have a gas, so it would be the density of the air. Now, since the ideal gas laws, PV is nRT, and density is going to be proportional to n, the number of moles, divided by the volume, that if you take n and divide by the volume, you would have P over RT. So here, this means that we're going to be proportional to 1 over T, the temperature. Now, so the temperature is going to be what's varying between the air above the road and the road surface. Now, pressure is going to be the same for the day, so we don't have to worry about pressure. So that means that n minus 1 is going to be proportional to 1 over T, and we can think of that as meaning that n minus 1 times T is equal to a constant. All right? So that gives us, say, n cold minus 1 times T cold is equal to n hot minus 1 is T hot. So we can basically look at this expression for the Mirage angle and we can get rid of one of these. We can get rid of, for example, the hot, or the, let's say the hot, let's get rid of the hot, the index of refraction, and then we'll have the temperatures. So this requires some algebra, some steps to do this. We have NC minus 1 times T sub C is NH minus 1 T sub H for hot. And then we can multiply it out. NC TC minus TC. And the hot index of refraction times T hot, temperature. And just remember that we're looking at the hot temperature near the road surface and the ambient temperature in the air. If you get a few centimeters away from the ground, you basically have air temperature. In fact, if you're on a hot summer day, you take your hand and you have to move it really close to the road to start feeling warm, and then you gotta be careful, you might burn your hand if you touch the road. So we're looking at these two. This is going to be a car, traveling, and here, when I see the Mirage, the cold is going to be up here, and the hot is going to be where, well, actually, it's going to be where the path of light actually got very close to the road surface. This here, I drew a nice diagram for you here. That shows it better. All right. Okay, so now when you get this, we can then play around with the math and say here, let's go ahead and look at TC, divide by NC, minus TC over NC equals NH over NC. This is going to be a nice, cute formula that we're deriving here. Divide by NC there. And then for the next step, let's go ahead and have this on one side of the equation. This is the N hot over the N cold times temperature hot. And that's going to be equal to Tc, what's on this side, minus 1 over Nc Tc. And then we can bring that to the other side. We're going to add that 1 over N. So this is just algebra to play around. So the next step is, since we're basically after this ratio, like that's like where I'm heading, say there, I want to divide by the th. So we have then here, just divide by the th everywhere, tc over th. And then the last thing, the th's will cancel, that I have here. The idea is to get this expression in terms of the two temperatures and just the one index of refraction, the N, the NC, the NC. So the next step is a little factoring. We'll have here the hot index of refraction over the cold index of refraction, cold temperature over the hot temperature. And this, remember, T's in kelvins. So if you have the Celsius, you have to add 273 to it. So what we have here, if we pull out the 1 over NC, we have a 1, we have here, and then we have with the minus sign, we have that. And then the next step, since we have a 1, subtracting this, let's go ahead and do that. 1 minus NH over NC. And that would be 1 minus, now we subtract. And here we subtract. All right, get that. And then here, watch this cool trick. This thing here is the same as this here, which means we can do another factoring and say 1 minus 1 over NC is 1 minus Tc over Th. And this is really neat because it basically has here your temperatures and the index of refraction, which is the cold index of refraction, which is the air, ambient air. So if we look at this, alpha, take the square root, we have the 2, and for the 1 minus this, we're going to just put all this in here. So we have 1 minus 1 over NC, 1 minus Tc over Th, and that's a nice formula. So this is the index of refraction of the air, the ambient air, and then this is the temperature, the cold is the temperature of the ambient air, and you divide by the temperature of the hot road surface. And for North Carolina, when I was making my trip, the ambient weather temperature was 88 degrees Fahrenheit, 31 degrees, same as 31 degrees Celsius. And if you add your 273, you get your 304 Kelvin. And the hot road surface, which I got from engineering articles where I could estimate it based on the temperature of the day, what the asphalt, what the temperature would be near the asphalt, very hot. Could be around 120 degrees Fahrenheit, which is 49 degrees Celsius, which is 322 Kelvin. And the index of refraction of air, we're going to study this more for homework, but 1.00026 for around the temperature that we're talking about. But for homework, you're going to be looking at this very carefully and fine-tuning this. But if we plug all these numbers in, then for the alpha, we get 2, 1 minus 1 over 1.00026. See, the index of refraction of air is almost 1. But now we need to have this more accurately. And then 1 minus the 304 over the 322. And when you plug all this in and use the calculator, you get 5.39 times 10 to the minus 3 radians. And then what you need to do is you need to go 180 degrees per pi rads. And then that's going to give you the angle, which is very small. Look, 0.31 degree. That's very small. And that's the Mirage angle, tends to be small. So for homework, you're going to be looking at this more carefully and doing some more work. And let's look at a video here of the paper I wrote involving the Mirage. And the idea that I got for the Mirage was that if you were driving in a car and the light's going to do this to get the Mirage effect, that I figured you could get this angle, this Mirage angle, alpha, by timing, getting closer and closer until the Mirage vanished. And I figured you could calculate this Mirage angle by knowing how fast the car is going and timing where this you get to the sign. So there's some sign here. You're seeing some, orange, some sign. So then when you get here, you can measure this distance. And if you measure this distance, you can then use geometry to get that angle. So you can actually measure it. This is the idea I had for the paper when I was on a trip, actually going back to the same place in North Carolina, Beaufort, North Carolina, where my dad was taking me as a boy many, many years ago. So we're talking 60 years ago to revisit. So it's fitting that the paper was written based on the Beaufort trip, since it was the Beaufort trip where I first saw the Mirage. In fact, my dad said it was a Mirage, and now, many years later, publication. So check out the experiment, the observation that led to the paper. This video is about the road Mirage. Note the two orange signs ahead. The car is maintaining a fairly constant speed of about 30 meters per second. The Mirage of an orange sign on the left will be shortly visible. There it is. It appears that the orange is reflected from the road off a layer of water. We are going to note when the Mirage of the orange sign vanishes. Now, every second we travel 30 meters. We are getting close to the sign, almost there. And as we pass the sign, we will note the distance, 480 meters. We will need the dimensions of the sign for our analysis. The low soft shoulder sign has the standard dimension of 3 feet for each side, that is 0.91 meter. Therefore, the vertical diagonal is 1.3 meters. By measuring the pixel lengths with a software graphics program and using length ratios, we arrive at 1.8 meters for the length of the support for the sign. Next, we will need the height from the ground of the observer in the car. When I took the video of the Mirage, I had my smartphone at about this height from the ground. Getting to 2 meter stick, 120 centimeters. 1.2 meters. Though refraction is the cause of the Mirage, we will approximate the Mirage as occurring from one single reflection from the road surface. We pick the lower part of the sign as the last rays from the orange sign reaching the eye. Taking the ratio of 1.8 meters to the sum of 1.2 plus 1.8, we arrive at the 288 meters from the sign to the point of reflection. The angle alpha is the Mirage angle. The tangent of alpha is 1.8 over 288. When you use a calculator to obtain the arctangent, you find that the alpha angle equals 0.36 degrees, a very, very small angle. Introducing refraction, the light bends away from the normal as it enters a medium with less index of refraction.
The index of refraction of air reduces as the air gets warmer. Note that n times sine of theta is a constant. For the Mirage, we have a gradient in the index of refraction. We have a cold temperature at the observer, the temperature from the weather station, and a hot temperature at the road surface, which value we find from engineers who study asphalt surface temperatures given the ambient weather temperature. Then the refractive index of air can be calculated in each case based on the temperature. Plugging in the values, you can solve for the angle theta and then find its complementary angle alpha. The calculated value is essentially the same as that found earlier. I would like to thank my dad for telling me about mirages when I was a boy on a family trip to Beaufort, North Carolina in 1961. Returning 58 years later, I shot the Mirage video. Also thanks to John Rideout, transportation coordinator at my school, for discussions on highway lane widths and signs. Finally, thanks to my lovely wife Margaret for driving the car for the video.